Pop quiz. When white light enters a glass prism, which color exits with the greatest overall bend? Red, green, or violet? Lock in your choice now. We'll reveal it in a moment. In this video, you learn how refraction bends light at boundaries, how dispersion separates colors, and how the minimum deviation condition links a prism's geometry to its refractive index. To begin, recall what refraction is. Refraction happens when light crosses between media at a non-zero angle and changes speed, so the path bends. The refractive index compares the speed of light in vacuum to its speed in the medium, and it depends on wavelength. That wavelength dependence drives dispersion. Next, let's connect this to prisms and deviation. Through a prism, the total bend is the angle of deviation, the angle between the income and outgoing rays. The deviation is smallest when the internal path is symmetric. In that minimum case, the refractive index equals sine of open parenthesis A plus delta minimum over 2 close parenthesis divided by sine of A over 2. Now we can circle back to our quiz. The correct answer is violet. Because the index is larger for shorter wavelengths, violet bends the most and red bends the least. Let's practice the minimum deviation equation with some numbers. Suppose a glass prism has a refractive index 1.52 and an apex angle of 60 degrees. Delta minimum equals 2 times arcsine of n times sine of A over 2 minus A. Multiply 1.52 by sine of 30 degrees to get 0.76. The arcsine is about 49.5 degrees. Double it and subtract 60 to get about 38.9 degrees. Before moving on, let's bust a couple of common myths. First, the angle of deviation in a prism is about refraction, not diffraction. Second, white light is not one wavelength. It is a mix of many wavelengths, which is why a prism separates it. So far, we've explored how refraction bends light at boundaries, how dispersion separates it by wavelength, and how the minimum deviation equation links refractive index and prism angle to the smallest total deflection. Ready to lock it in? Tap the link for study guides and flashcards on this topic, so you can keep learning without missing a beat. Now apply the same steps to a nearby wavelength. If the index for blue light, n, is approximately 1.53 with the same apex angle, the calculation gives a minimum deviation of about 40 degrees, roughly 1 degree more bend than for red. Zooming out, these ideas also explain natural phenomena. In water droplets, sunlight refracts in, reflects once inside, and refracts out again. Rays bunch up near the minimum deviation angle for each color, creating the bright primary rainbow. Halos around ice crystals in the sky come from a similar refraction and deviation story. To keep your problem solving on track, remember a few tips. If the internal path is not symmetric, the deviation is larger than the minimum. Changing the apex angle shifts the value of the minimum deviation. And the same equation works in reverse. Measure the minimum deviation and the apex angle, and you can solve for the refractive index. Here's your 4-step recipe. 1. Sketch the prism and mark the apex angle. 2. Decide whether you are solving for the refractive index or for minimum deviation. 3. Plug your numbers into the minimum deviation equation and work carefully with your calculator. 4. Interpret the result physically. In the same prism, violet should bend more than red. To recap, refraction bends light, dispersion makes colors separate, and minimum deviation happens on the symmetric path inside the prism. Its equation connects the refractive index, apex angle, and the smallest total bend. In ordinary glass, red bends least and violet bends most. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.